Let's begin lecture number 6, that is evolutionary process 3. So as we already discussed that the limitation of the previous sub-objective is we directly targeted the uniform magnetic field instead of reconfirming it whether that is the optimal objective function to decide that it is to decide it mitigates lateral misalignment problem. So later we understood that let's try with uniform induced voltage as the target objective, and let's find what would be the optimal magnetic field strength, whether it would be uniform magnetic field which we have previously targeted, or it would be something else. That's what we are going to see in the sub-objective 3. Now you can see in this evolutionary process 3, the figure number 40 is the, let us say, generic what we call transmitter and receiver coil figure. So you can see the red one is the transmitter coil, let us suppose, and this green color one is the receiver coil, a small receiver coil you can see. So this is a perfectly aligned receiver coil, and the dotted one is the misaligned receiver coil. So the transfer distance is here, over here is D, and the dimension of this receiver coil is 2a by 2a over here, let us suppose. So from equation 14, whatever you can see over here is simply is nothing but a Faraday law of electromagnetic induction. So what is the meaning of that is, let us suppose we already know the induced voltage V is nothing but product of H and A. So this Hz of x comma y is the magnetic field strength, and the dA is the differential area, and double integral of A, that is that gives the total effective area of this receiver coil. So effective area of this receiver coil is given over here. So now you can see this equation 14, the limits for this particular equation are from minus A to A for both along x and y direction. The reason is, under perfectly aligned condition, the receiver coil, as I already said you, the dimension is 2a, so it would be minus a to plus a along x as well as minus a to plus y along y. So that's the reason the area vector would be, the limits for the area vector would be minus a to a in both the directions, Hz x comma y dx and dy. And whereas j omega mu naught nr is nothing but omega is the angular frequency 2 pi f, mu naught is the permeability in free space, because these receiver and transmitter coils are located in free space, where nr is the total number of turns concentrated in the receiver coil. Now equation 15 signifies the effective area of the receiver coil. You see, generally my area can actually slide from this point to this point, any point it can be like. So it can be from minus infinity to infinity. So let us say it is AR x comma y is the actually the area vector of this, and dx dy. Now let us suppose we know that when it is when the dimensions, when my area vector is relying on minus a to a, when the x limits is from minus a to a, or my y limits is from minus a to a, it represents 1, and otherwise it is 0. That means when it is perfectly aligned, then total amount of magnetic field is captured by the receiver coil. The moment there is a misalignment, what happens is, when it is moving away from the limit of minus a, outside minus a or outside a, then the effective area becomes 0. So that's what is equation 15. So equation 16 is very interesting equation. If you substitute this dA in equation 14, then you will get the misaligned receiver coil, because I want to sweep this receiver coil from minus infinity to plus infinity, or I want to slide the receiver coil from minus infinity to infinity, both in x and y direction. So my limits for misalignment would be minus infinity to infinity in x and minus infinity to infinity in y. Now the function, you can see interestingly, this function v is become a function of delta x comma delta y. Delta x is nothing but misalignment along the x direction, and delta y is misalignment on y direction. That misalignment can be clearly seen in figure 40. You can see, for a perfectly aligned receiver coil, it is 0 comma 0 comma d is the position of the receiver coil, and for a misaligned receiver coil in P2, you can see it is delta x comma 0 comma d. That means this is misaligned along the x direction, along the x axis, at delta by delta x units. So similarly, it can also be misaligned at delta y. It can also misalign both delta x and delta y, that is diagonally also. So this expression, equation 16, gives a generic misalignment, induced voltage of the receiver coil under misalignment state. And equation 17, as you can see, g of x comma x dash comma y dash is equal to convolution of two functions. Whatever result you are seeing over here is simply identical to equation number 16. If you compare equation 16 and equation 17, you'll understand that the induced voltage, whatever we are determining under the misalignment condition, is nothing but the convolution of the magnetic field and a receiver coil, the area of the receiver coil, let us suppose. So if you convolve these two functions, you will get induced voltage. Instead of using the equation 14, one can also use the convolution of these two functions to determine the induced voltage. So that is one of the contribution that we have given in this through this evolutionary process 3. And once, because in this what we call, in this evolutionary process, we are already fixing my induced voltage V of delta x comma delta y to a fixed value, because we are targeting a constant induced voltage. So the target we can select. So the target is user friendly, and the area vector is nothing but the area of the receiver coil. So if you are using a square coil, then it becomes a rectangular function. The area vector of AR becomes a rectangular function. So that also is a user friendly. That means a user can define it. Now Hz x comma y is what we need to find. So if we apply Fourier transformation on equation 18 in both the sides, the convolution symbol will remove and it becomes a pure multiplication. Then we can actually try to find Ft of Hz comma x comma y is nothing but the ratio of Fourier transformation of induced voltage to the Fourier transformation of area vector. Then the Hz x comma y can be determined as inverse Fourier transformation using equation 19. So equation 19, I think it is very simple to understand. Now once we understood mathematically how to determine the Hz x comma y, now we will understand like what we have targeted. Now let us suppose you forget about what is equation 20. It is a generic formula of the optimal magnetic field strength, which you may not understand from equation 20 at this moment. But I can 100% guarantee you that if you carefully listen what I am saying right now, using these exemplary designs here, both the figure 41 and figure 42, you will clearly understand what I mean to say. So in figure 41, you can see this minus 2A to 2A, I want a constant induced voltage. So as I want a constant induced voltage, this becomes a rectangular function from minus 2A to 2A. And my receiver coil is a square coil, therefore I want my square coil to be from minus A to A location. I already said you that the receiver coil is selected as minus A to A because its maximum dimension is 2A in both the sides. So it becomes minus A to A under perfectly aligned condition. Now I know these two quantities, that is the area vector AR and the target induced voltage, which I am targeting. So what I don't know is this magnetic field strength. That you can see I have put a question mark over here. So we need to determine this using what? Using equation 19. Then what I found is when I do the evaluation of this, because this is a rectangular function of minus 2A to 2A, so I know how to write a rectangular function, and I also know how to determine the Fourier transformation of rectangular function. You will get a sinc function. Similarly, you can do find the Fourier transformation of rectangular function of area vector from minus A to A, and that also will get a sinc function. If you divide and you find the inverse Fourier transformation, you will get a constant Dirac functions over here. You can see that. So those Diracs you are getting for this particular target, that is minus 2A to 2A, you are getting at the location minus A and A. That means if you generate a constant Dirac functions or the impulse function, impulse magnetic field strengths at locations minus A and A, then you will get a constant induced voltage from minus 2A to 2A. So this is completely different from what we were previously targeting, that is the uniform magnetic field. So here a highly concentrated magnetic field needs to be generated at the locations minus A and A to get a constant induced voltage from minus 2A to 2A. That is what we have got. Now this equation 20, what it says is, here instead of we targeting 2A minus 2A to 2A, we have actually targeted minus NA to NA, where N can be any number. See, some people will target from minus A to A, some people will target from minus 3A to 3A, so some will target from minus 5A to 5A. So accordingly, we have taken as minus NA to NA, so that we can give the users according to their wish, they can determine. So this equation 20 gives the generic formula for both odd functions and even functions. Odd functions is nothing but, if you see, this is minus 2A to 2A is an odd function, and if it is minus A to A, it becomes odd function. Sorry, minus 2A to 2A is even function because n equal to 2 is a even number, and if n is equal to 1, that is minus A to A or minus 3A to 3A, becomes an odd function. For both, you will get these as the equations. What we have done is that we have substituted in equation this in the MATLAB, and we have got this equation. Now analytically we understood from this slide. Now we will understand graphically what is happening actually. Now let us slide the receiver coil from minus 2A to 2A. What is happening, we will see. When the receiver coil is positioned at minus 2A, then the dimension, it would be from minus A to minus 3A. That means this would be minus 3A, this corner point, and this would be minus A. So at minus A already there is a constant Dirac, right? So it is actually receiving the magnetic field strength, right? My receiver coil is able to capture that. Now the moment it misaligns to minus A, still it is receiving the same amount of magnetic field strength, which is located at minus A. Now when it releases out from minus A, let us suppose it just released out of the minus A, then what happens is, it will start getting magnetic field from the A location. That is the magnetic field, the highly concentrated impulse magnetic field strength, which is located at A location, will actually try to generate it. So in this way, it is still maintaining the same amount of induced voltage. As you can see, minus 2A, it has same amount of magnetic field. From minus 2A to minus A also, you have the same amount of magnetic field. From minus 2A to 0, right now it is in the 0 position, then also you will have a same amount of magnetic field. So in this way, till my receiver coil, when it reaches to 2A location, I will get a constant induced voltage. That's the reason I am getting a constant induced voltage from minus 2A to 2A. So I hope with this explanation it became very clear, like how a highly concentrated impulse magnetic field strength is actually giving a constant induced voltage from minus 2A to 2A, or whatever target you target. If you target from minus 3A to 3A, then you will get 3 impulses at the location minus 0, I think, minus 2A and 2A. Now you can also see in figure 44 the 2D diagram. So whatever I have shown in the previous diagram is a single one-dimensional diagram. So now you can see in 2D also. Now in 2D it is much more clearer. The induced voltage should be actually in this format, the rectangular cuboid shape you can see, right? So that is the actual target induced voltage, and the black one you can see as the arrow marks over here. These are the concentrated magnetic fields you need to generate at these locations. A highly concentrated magnetic field needs to be generated to get this cuboid induced voltage at the receiver coil region. This is for n is equal to 2, that is minus 2A to 2A. Now if you want to generate for n is equal to 3, then you need to have a Diracs in this format, as we can see in figure 44b. Now what we understood is, the problem with figure 44 is it is an ideal case. The first thing is generating these ideal signals, this ideal concentrated magnetic field, as you can see in these black arrow marks, is impossible, because we cannot generate Dirac functions at any cost. The reason why we are getting Dirac signals as the answer is, see, you can see there is a sudden change from the induced voltage from very maximum to minimum at very instant. So practically, if I'll just go back, practically at the induced voltage can never decrease from maximum to minimum at the same position, that is here minus 2A. That will never happen. There should be a slight roll off, a gradual decrease should happen. So that's the reason in figure 45, instead of targeting a rectangular function, we have given a roll off. You can see over here a slight roll off we have given. Because of that roll off, what we have understood is, instead of getting a concentrated magnetic field set or Dirac functions, we have got a Gaussian curves, a Gaussian magnetic field like this. So I hope you understood. So these Gaussian curves have been optimized in the MATLAB. So directly now I'll move on to let us say figure 46. Sorry, okay, table 5 I'll explain you. Now you can see at these locations, these are the locations where we need to generate the concentrated magnetic fields. These are the 4 quadrants you can see here. Now how I got this minus 51 to 51 and these things is, this is nothing but the receiver coil dimension is total dimensional length is 100. So minus 52 plus 50 it should be there. So why we got minus 51 is, we need to slightly adjust it because of the negative magnetic fields we generate due to the receiver coils. So the locations are slightly adjusted. Instead of minus 50 comma 50, it is minus 51 comma 51. For n is equal to 2 design, similarly n equal to 3. Now figure 46 is, this is the layout of the 2x2 transmitter coil, and figure 47 shows the magnetic field strengths of n is equal to 2 and n equal to 3 design, both. Now you can see this is a highly non-uniform concentrated magnetic fields at those locations. Because of this highly non-uniform concentrated magnetic field, I am getting figure 48 as constant induced voltage. Now I just want to explain how it is happening is, in figure 47a, under perfectly aligned condition, each quarter of this magnetic field is actually contributing the receiver coil to form an induced voltage. The moment there is a misalignment along x, y or any or even the diagonal direction, how much ever it is losing from other parts of the magnetic field, concentrated magnetic fields, the same amount will be gained at the other parts. So in this way we will get a constant induced voltage, as you can see in figure 48. So figure 49 shows actually the measured and simulated data of the magnetic field profiles using a near field coil. This is the near field coil. So what we do is, we generally sweep the near field coil. So we will measure the S parameters, so which resembles same as the magnetic field profile, because the size of the near field coil is very small. So it is actually giving the points at which magnetic field distributions are concentrated. So figure 49, this second the right side graph is showing the efficiency, the normalized efficiency. This is, so if you compare to the literature design, the n equal to 2 design is reduced by 19.89%. See, the reason is the dimension. Previously the literature design is 200 by 200, but whereas the n equal to 2 design is almost like 186 millimeter. So 14 millimeter is actually reduced in one dimensional. So because of that, the net reduction in the area has been 19.89%. And also misalignment tolerance is improved by 293%. So because of this non-uniform magnetic field strength, there are two advantages. One is reduced dimension, and the second is improved misalignment tolerance. Whereas for n equal to 3 design, the misalignment tolerance is improved by 688%, which is very more. So the proposed non-uniform magnetic field distribution using proposed analytical framework is so far the best possible design to mitigate the lateral misalignment problem. So what are the conclusive demerits of the sub-objective 3 is, the proposed design still accounts a large leakage flux irrespective of its excellent misalignment tolerance. So the problem is leakage of flux irrespective. Let us suppose if it is perfectly aligned, then there is a large part of flux which is actually concentrated at the receiver coil region is actually not coupling with the receiver coil, so the efficiency is getting reduced. So this flux leakage is reduced in the further evolutionary processes. So with this I want to end the lecture number 6. Thanks a lot.